Hey everyone, welcome back to Linear Algebra. This is going to be lecture 16 of the course. And in this section, we are going to get into the topic of linear independence and the contrary topic, linear dependence. So let's go ahead and jump into it. Okay, so this will be section 4.4, and we'll call it linear independence. Okay, so I think, we'll see a bajillions of examples. I think it's best in the case of linear independence to just lead with the definition rather than a motivating example and talk through the definition and then jump into a bunch of examples. Linear independence is a fairly straightforward idea, I think, but some of the details can be a little bit dizzying, especially if, this is kind of your first go round in linear algebra. So let's go ahead and define it. So we'll let S be a subset of a vector space V. Okay, as per usual. Now this definition is going to actually have 4 parts. Okay, so the first part is kind of the meat of the definition, and then the other 3 parts are going to be sort of special situations where the definition may have to be altered slightly. So we'll start with part 1. So if S has at least 2 elements, if S has at least 2 elements, then S is linearly dependent. Okay, S is linearly dependent if and only if for some V in S, for some vector in the subset S, V, the vector, can be written, can be expressed as a linear combination of the other vectors in S. Okay, so as I said, this is kind of the meat of the definition. So S is some subset of a vector space V, and we say that S is linearly dependent if and only if there exists some vector in S. It could just be one of them, it could be many of them, but at least one vector in S such that S can be expressed as a linear combination of the other vectors in S. Right? If I can write V as a linear combination of the other vectors in the subset, then the subset is linearly dependent. Okay. Okay, and so that's the meat of the definition. Let's talk about some of the other pieces. So what if S has just one element? Right? So if S equals just a single element, well, then S is, again, definition is linearly dependent, right? So S is linearly dependent if and only if that vector, that one vector in S, happens to be the 0 vector. Okay. Right. So if S is a singleton subset, then it's linearly dependent if and only if that vector in S, it happens to be the 0 vector. Okay, and then the third case, well, we've talked about when S has more than 2 elements. When S has 1 element, what if S is empty? Well, if S equals the empty set, then S is not linearly dependent. Okay. And then, of course, the chapter's called linear independence. So what does that mean? Well, it just means not linearly dependent. So we say S is linearly independent if and only if S is not linearly dependent. All right, so it's kind of a binary, right? You either are or you aren't. Okay. Okay, perfect. Right, so as I said, part one is the meat of the definition. So basically, what does it say? It says a set S is linearly dependent whenever it contains a vector that can be written as a linear combination of the other vectors in S. Okay, right, so if it's possible for me to take any vector in S and write it as a linear combination of the others, then S is dependent, linearly dependent. All right, so let's crank out a bunch of examples here so we can think this through, really see something concrete here. So let's start with kind of the simple example. So let's let S equal I, J, K, right? Unit direction vectors in R3, we'll say. Okay. Then is this an independent set or a dependent set? S is a linearly independent set. Linearly independent set. Right, and this is pretty easy to see, right? If you just take one of the vectors, let's say 1, 0, 0. Well, I mean, in order for it to be dependent, we're going to have to be able to find coefficients A and B such that 1, 0, 0 is equal to A times 0, 1, 0 plus B times 0, 0, 1. Right, and that basically means that we're looking for some vector of the form, let's see, 0, A, B. Clearly, this is never going to work out, right? There's never going to be there's no other vector, right? That you know, these two are not compatible, right? So no such AB exists. Okay, so, and you could do the same exercise for the others, right? You said try to write J in terms of I and K. You'll see that you can't. There are no coefficients. No constants that can be plugged into a linear combination to make J equal to I plus K, or K equal to I plus J. Right? So it's a linearly independent set. Okay, and in general, this holds for Rn, right? So let's let S equal the set of, you know, E1, E2, En, all the unit direction vectors in Rn. Okay, S is linearly independent. Okay, for the same reasons, basically for the same reasons as the previous example. Okay, so these are two crucial examples of linearly independent sets. Okay, let's take another example where we look at the, sorry, 1 second, pages here, where we take a look at, you know, a linearly dependent set. So let's consider S, and this will be the set of vectors 1, 2, 3, 4, 5, 6. I'm sorry, 4, 6. Okay, and this is obviously a subset of R2. Okay, so 1, 2, 3, 4, 4, 6. Okay, so is this linearly independent, linearly dependent? Well, we can see pretty quickly that it's actually linearly dependent. S is linearly dependent because, all right, here's one reason. I can take the vector 4, 6, and I can express it in terms of these other two. Right, so I can say A times 1, 2 plus B times 3, 4. If A is equal to B is equal to 1, then this works out, right? Right, so this would be 1, 2 plus 3, 4. 1 plus 3 is 4. 2 plus 4 is 6. Right, so 4, 6 can be expressed. So specifically, 4, 6 can be expressed as a linear combination of the other two vectors in S, right? And so that's the definition of linearly dependent, okay? And so what is this? One kind of interesting way to think about this is to think about this geometrically. And so in the case of vectors in R2, it's really easy to draw them. So, okay, so let's see here. So we'll just make it kind of small. Hopefully it's not. Hopefully we can interpret this, but let's just kind of mark off the x and y axis here for a few values. And so let's put in the first vector 1, 2, right? So it's 1 over 2 up. You can think of it like right here. So that's that guy. And then let's add 3, 4 to it, right? So 1, 2, 3, 1, 2, 3, 4, and we get up to here. Okay, so this would be 3, 4 right there. And so you can see that this is actually 1, 2 plus 3, 4 geometrically will get you to the same place as 4, 6. Right? So 4, 6 would be 1, 2, 3, 4 over, 1, 2, 3, 4, 5, 6 up. Right? And so you could express that same vector geometrically as the sum of the other two in S. Right? So geometrically, we can arrive at 4, 6 using a linear combination of 1, 2, and 3, 4. Now, if our coefficients had been other than a, b equals 1, you'd see that all that means is that some of these vectors are being stretched or shrunk, whichever the case may be, stretching or shrinking them. Right? And so we can get to 4, 6 using the other two vectors. Okay, and so that's sort of geometrically what happens when you have a set that's linearly dependent. Okay, let's take a look at another example. How about let's let S equal 1, -1, 2, and -3, 3, -6. Right, so this is a subset of R3. So is this a linearly independent set or a linearly dependent set? Well, just a little bit of work will show you that this is linearly dependent. Right, and it's linearly dependent because the first vector, 1, -1, 2, is actually a scalar multiple of the second. So it's actually equal to -1/3 of this guy. Right, so 1 is indeed equal to -1/3 times -3, and -1 is equal to -1/3 times 3. Right, so you can see that this is we're able to express this guy in terms of this guy. Okay. Now in this case, because the size of S is exactly 2, linear dependence occurs whenever basically any of the vectors is a scalar multiple of the other. So linear dependence boils down to one vector being a scalar multiple of the other. Okay, so good examples of linearly independent and dependent sets. Okay, so we should have a good, reasonable intuition about what we mean by linear dependence and linear independence. Okay, so let's talk about another way, kind of an alternate way to think about linear independence. So an alternative characterization of linear independence. Okay, so you can kind of think of this almost as a almost as a definition. So we'll say a set S in a vector space V. Okay, a set S in a vector space V is linearly independent. It's linearly independent if and only if there is no V, no vector in the space or in the set S, no V in S, such that V is in the span of S minus V. Okay, and I know I probably lost you on that one. Let's talk this through a little bit. What is, first of all, what is this notation here? What the heck is span of S minus V? Well, you think of S, you know, S is maybe the set of vectors V1, V2 through Vn. Okay, so it's a set of vectors. If I were to subtract one of the vectors from V, so let's say I subtract V1 from S, right? So if I subtract V1 from S, one way to notate that, so if I subtract V1 from S, I can notate that as, you know, the set S minus V1. Right? If I remove it, right? If I remove V1 from S, right, then this is one way to notate that. And you can kind of just, I mean, that basically is just V2, V3, dot, 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 Vn, right? Just basically take that one element out. This is just notation. Okay, and so what is this definition saying then? Well, if you have a set S in a vector space V, that set is going to be linearly independent if and only if there is no V in S such that the removal of V from S, nonetheless, we retain V in the span, right? Even after I remove V from S, right? So let's break this down a little further. Okay, let's break this down. Because this is a key point. This is very key. All right, so let's say, let's let S equal V1 through Vn. Okay, it's a subset of a vector space V. Okay, and just for simplicity, let's say that, let's let the span of S equal some set A. Right, so you've got a subset of S, and then you've got the span of S, which is bigger, right? You're going to reach outside of S, and there'll be more vectors that you can write as linear combinations of S. Right, so just to keep that straight, I've got some S subset, and then I've got the span of S, which I'm calling A, just for now. Okay. So if S is linearly independent, and I remove Vn from S. So here's a couple cases. So if S is linearly independent, okay, and I remove Vn from S, so I'm saying let's remove the last vector here. What happens to the span of S? Well, what happens is that the span will be smaller. Okay, so the span of S minus Vn is going to be a proper subset of A, a proper subset. Okay, so in this case, right, I've got my S. Okay. Now, if I were to remove some vector V, cross it out of S, right? then, you know, this whole thing might have been the span of S, right? But once I remove this vector, there are some vectors I can't get to anymore. And what I'm left with is the span of S minus Vn, right? So let's say I crossed out Vn. Right, so if I remove a vector from a linearly independent set, then that's going to constrain the span. It's going to make the span smaller. Okay, and in fact, one of the vectors you would lose from the span would be Vn. So Vn would not be in the span of S minus Vn. Okay. All right. So that's in the case where S is linearly independent. But if S is linearly dependent, the situation is quite different. Okay. So if S is linearly dependent, right? If S is linearly dependent and Vn happens to be the vector, let's just assume without loss of generality probably that Vn happens to be the vector that can be written as the linear combination of the others, right? So Vn is somehow redundant, right? If I can write Vn in terms of V1 through Vn minus 1, then Vn is redundant in the set S, right? And so if S is linearly independent and Vn can be written as a linear combination of V1, Vn minus 1, right? Then what happens to the span if I remove Vn? Well, the span of S minus just that Vn vector, that redundant vector, well, it's still equal to A, right, which is the span of the original, right? So the removal of a linearly dependent vector from a set doesn't impact the span, right? And then clearly Vn is still in the span, right, because it can be written as a linear combination of the vectors that remain, of these guys in particular. So Vn is in the span of this smaller set. Okay. Okay. So that's, you know, that's a pretty sophisticated way of thinking about it, right? So I mean, basically, what are we saying? We're saying that we can still get to all the vectors in A by using just V1 through Vn minus 1. Right, so that Vn vector really truly is redundant. That's sort of what linear dependence means. It means you've got a redundancy. There's something else that you don't need. Now, one way to kind of visualize this is to think of the fact that V1, V2 dot 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 Vn, right? If I take the original S, it's kind of the same thing as V1, V2, you know, dot 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 Vn minus 1, comma, and then whatever the linear combination of these guys is that gets me Vn. So like A1 V1 plus A2 V2 plus dot 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 plus An minus 1 Vn minus 1. Right, so this guy here that's just Vn. Right, so it doesn't need to be in S to still have the span of S be the same. Hopefully that's clear. All right, so including Vn in S is redundant if I can write it as a linear combination of the other items in S. Okay. Right, and so that's where that definition came from. So a set S in a vector space V a set S in a vector space V is linearly independent linearly independent if and only if there is no V in S. There is no V in S such that V would be in the span of S minus V. Because remember, you know, if the span of S minus V is smaller than the span of S, then the first vector to go is V, right? V is gone, right? But if the span of S minus V is the same as the span of S, then naturally V will remain. Okay, kind of another way to write this, right, in terms of dependence, which some people tend to think is possibly better, would be to say a set S in a vector space V is linearly dependent a set S in a vector space V is linearly dependent if and only if there is some V in S such that V is in the span of S minus V. Right, so S has to be linearly dependent if there's some vector in V that, you know, still in the span even after I remove it from the set S. Right, meaning it's redundant, meaning it's captured by the other ones already. It's not really, you don't really lose access to that vector. It's just not one that's explicitly written in S. Okay. Okay. All right, so again, kind of a different characterization of linear dependence and independence. Okay, so how can we test for linear independence? Right, so the examples we looked at, I mean, we just kind of eyeballed them. They were small, simple subsets of, you know, like 2 or 3 vectors, and we can easily see whether there is or is not a linear combination. But in general, like, what are we looking for when testing a set for linear independence? Well, here's the theorem. Okay, so let's let S equal a set of vectors v1, vn, and this is going to be a non-empty finite subset. Talking finite for now. So we'll let S be a non-empty finite subset of a vector space V. Okay. So we say S is linearly independent. So then S is linearly independent. Right, so it's independent if and only if the equation, okay, so take all the vectors in S, A1, and create a linear combination. And set it equal to the 0 vector, right? So if the equation a1 v1 plus a2 v2 plus dot 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 a n vn is equal to 0, right? So if, all right, so S is linearly independent if and only if this equation implies that a1 equals a2 equals an equals 0, namely all of the scalars in this linear combination are 0. Okay. Okay, right. So this is kind of the key way to test for independence, right? If I'm given a subset S of a vector space, and I mean, I can always just crank out this equation quick, and if this equation has only coefficients of 0, i.e. solution of 0, then S must be linearly independent. Okay, and we're going to prove this theorem because this is kind of an important one, and also it's not too tricky, I don't think. I think it's pretty straightforward, actually. So let's go ahead and prove it. All right, we'll start with the case where S is greater than or equal to 2. All right, so we'll so case 1, S, the size of S is greater than or equal to 2, right? So there's at least 2 vectors in the subset. Okay, and we'll go this direction. We'll assume S is linearly dependent. Okay, we'll assume S is linearly dependent, and we'll show that at least one of the coefficients is non-zero. Okay, so assume S is linearly dependent. Okay, so if that's the case, then there exists some VI in S. Okay, some VI in S such that VI is going to be in the span of S minus VI. Right, that's just the definition we just sort of ran with. Okay, all right, so we're assuming S is linearly dependent. Then one of the vectors in S, call it VI for now, is going to be in the span of S minus VI. Right, it's redundant. Now, without loss of generality, let's just write VI as V1. Okay, so without loss of generality, let's let this hypothetical vector be the first vector that we'll write in the linear combination. And that's really, I mean, not an important point. You can make it the 3rd or the 10th or whatever. The first is attractive because it just makes the notation more straightforward, a little less clunky. All right, so we're going to assume without loss of generality that the VI vector that can be written as a linear combination of the others happens to be V1. Okay. Okay. So assume VI equals V1, which means, what does it mean? What does that mean? Well, it means that V1 can be written as a linear combo of the other Vn minus 1 vectors in S, right? And so specifically, what does it mean? Well, it just means there's V1, that vector, is going to be equal to A2 V2 plus A3 V3, however many there happen to be, plus dot dot dot, plus AN Vn. Right? V1 is the one that can be written as a linear combination of the others, so that means this is true. Okay. And now some simple algebra here can basically get you what you're looking for. Let's just subtract V1 from both sides of this expression. And so V1 minus V1 equals negative V1 plus A2 V2 plus dot 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 plus AN Vn. All right, now what is this over here? Now I've got the 0 vector, and that's equal to negative V1 plus A2 V2 plus dot 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 plus AN Vn. Right, and so are we done? Yeah, this is it, right? Like, so what do we have here? A1 must be equal to negative 1. Most important, it's not equal to 0. Right? So therefore, A1 is non-zero, and we can see that this equation, you know, A1, V1, A2, V2, dot, 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 AN, Vn equals 0 does not imply that all the coefficients are 0. So A1 is equal to negative 1, which is not equal to 0, so not all of the AIs are equal to 0. right? And so that gets you the one direction. Okay. What about the other direction? Okay, so that gets you the one direction. What about the other direction? Well, the other direction we have to assume, let's assume we have a1 dot 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 an such that 0 equals a1 v1 plus a2 v2 plus dot 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 plus an vn. Okay. And some at least one of these AIs is non-zero. Right, so AI is not equal to 0 for some I. Okay. Okay, and so let's say that, well, what does that mean? Well, let's write it like this. Let's pull the AI out and put it on the other side here, right? So, well, let's just do it in order so people can see how this is working. So 0 equals a1 v1 plus a2 v2 plus dot 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 plus an vn, right? We start with this, right? Now some AI in here has a non-zero coefficient, so let's isolate it and pull it on the other side. So it'll be negative ai vi equals a1 v1 plus a2 v2 plus dot dot dot. Now remember we got this gap in here, so let's write it in there. ai minus 1 vi minus 1 plus ai plus 1 vi plus 1 plus dot 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 plus an vn, right? This is just basically I just plucked it out of here and threw it on the other side. Okay, now let's divide this down, right? Let's divide this down, right? So vi is going to be equal to a1 over negative ai times v1 plus, and we can do the same thing here, right? And now I'm just going to skip the gap, but remember the gap is still there, so it doesn't matter. An over negative ai vn, right? Okay. Right, now I couldn't do this if ai was 0, but since ai is not 0, this is fine. Okay, so what does this mean? It means vi can be written as a linear combination. So it can be specifically written as a linear combination of v1 dot 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 vi minus 1 vi plus 1 dot 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 vn. Okay. Right, and if that's true, then it's in the span. Vi must be in the span of whatever S is minus Vi. Right, does that make sense? Okay, so Vi is in the span of S minus Vi, and S is linearly dependent. Okay. All right. Okay, and so that's case 1, kind of the hard case, where S is greater than or equal to 2. Let's consider the other situation that can occur. So in the special case where S is equal to a simple one single vector, well, we know, right, that S is linearly dependent if and only if the vector in S is the 0 vector. Okay, so in the special case where S is equal to V, S is dependent if and only if the vector is equal to 0, right? And if this is true, if the vector is equal to 0, then obviously A1 V1 equals 0 is fine. I mean, this implies that A1 it must be 0. Okay. Oh, A1. Sorry, this implies that A1's doesn't necessarily need to be 0, right? And so you have dependence. Okay, because V is 0, right? So there's gonna, basically any A will work for A1. Okay. So if S is the singleton vector, then it's dependent if and only if the singleton vector is 0, and in that case, A1 does not have to be 0, right? Does not imply that A1 is equal to 0. Okay, so that's the other case, right? And so we did say that S was non-empty, right? So we don't have to worry about the empty set. Okay, perfect. All right, so kind of again, some of the wrinkles in some of these ideas can be a little bit twisty, but let's do an example here. This will be kind of a motivating example for a method that we're going to use. So let's let S equal 1, -1, 0, 2, 0, -2, 1, 0, 2, 0, -1, 1, right? And so it's this subset of 3 vectors from R4. Okay, now let's consider what a homogeneous system built on these 3 vectors. So A times 1, -1, 0, 2 plus B times 0, -2, 1, 0 plus C times 2, 0, -1, 1 equals 0, 0, 0, 0. Okay. Right, and so what we'd like to be able to do is test for linear independence by using this idea that A, B, and C have to be 0, right? That this equation here implies that A1 through, well, A, B, and C in this case, A, B, and C must be 0 in order for S to be linearly independent. Now, what's a quick way to kind of test such things, right? As is, this is very challenging to kind of, I mean, what are you going to do? Systematically sort of guess and check? No. So one of the things we can do is we can plug this into a matrix and use row reduction, right? So 1, -1, 0, 2, 0, -2, 1, 0, 2, 0, -1, 1, and then this is an augmented matrix 0, 0, 0, 0. Right, and you can pause the video, row reduce this, and when you do, you'll see you'll get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then all zeros at the bottom. Okay, and what does this imply? Well, here's your variable A, here's your variable B, here's your variable C, 1, 1, 1, 0, 0, 0, A, B, C have to be 0. Okay, so from this, we can see that A equals B equals C equals 0, right? And so that's the only solution. Remember, this is what we call the trivial solution to this homogeneous system. So we can see A, B, C equals 0 is the trivial solution. And it's obviously the only solution, right? And this is going to imply that A, B, and C, or all the coefficients in this equation, have to be 0, and so S is linearly independent. Right, that's kind of what that last theorem boils down to. It sort of boils down to looking at the solution space to a particular homogeneous system. Right, and so that's sort of the best method that we have for testing for independence. In the case where it's not obvious, like in the earliest examples that we did, where you only have 2 vectors and one of them is clearly a scalar, multiple of the other, you don't necessarily have to go through this. But in a case where like this, where it's not obvious whether some of these vectors can be written as others, this is going to be the most efficient approach. Just plug it in to this kind of a matrix and run it. Okay, and so here's the method it actually can be simpler than this. You don't actually even need the scalar portion of the augmented matrix. Right? The method is going to be one. Let's create the matrix A, whose columns are the vectors in S. Step 2, row reduce A to find B. Right, so find B equal to the reduced row echelon form of A. Okay, and step 3 is to just kind of give it a glance here. So basically what it boils down to here is I'm going to need a pivot in all 3 columns, aren't I? If I just have 2 pivots and 2 rows of zeros, that means I got a dependent variable, which means I have infinite solutions, not just the trivial solution. So I need a pivot in all 3 columns, right? And so basically I need a pivot in every column of A. So if there is a pivot in every column of B, right, remember B is the reduced row echelon form of A. If there's a pivot in every column of B, then S is linearly independent. Otherwise, it's not. So else S is linearly dependent. Okay. All right, so that's fairly straightforward, right? That's a pretty straightforward method. Okay, let's crank out a couple of examples using that. So example, is S equal to 3, 1, negative 1, negative 5, 2, 2, negative 5, negative 2, 2, and 2, 2, negative 1. Subset of R3. Is S linearly independent? Again, these are not obvious vectors. The scalars for representing one by the other two are not clear, not obvious. So let's just plug it into a matrix. So 3, 1, negative 1, negative 5, negative 2, 2, 2, 2, 1. Right? You don't need the zero portion of the augmented matrix. You just need what amounts to the coefficient matrix. Row reduce this, and when you do, you get the 3 by 3 identity matrix. Now please pause the video, double check that you can get to this. Right? Just in the interest of time, we don't want to be doing row operations and actually going through the steps, but this is just a calculation, right? So, but once you get to this point, you can see, yes, indeed, I got a pivot there, I've got a pivot there, and I've got a pivot there, right? So because there is a pivot in each column, S must be linearly independent. Perfect. Okay. All right. Let's do another example. This will be a nice kind of motivating example for a quick corollary. So let's let S equal 2, 5, 3, 2, 4, negative 9, and negative 8, 3. This is obviously a subset of R2. Is S linearly independent? Question. Okay, is it linearly independent? Let's see, how do we check? Well, we throw this all into a matrix and we row reduce it. 2, 5, 3, 2, 4, negative 9, negative 8, 3. All right, so I've got a 2 by 4 matrix. If I row reduce that, you know, so spend some time doing that. What you get is 1, 0, negative 55, and 65, 0, 1, 38, and negative 46. And so what does this tell me? Well, I've got a pivot here, and I've got a pivot here. I do not have a pivot here. I do not have a pivot there. Right, so I've got 2 pivots. I need 4 in order for this matrix to, in order for the reduced row echelon form of S as a matrix to produce a result that's telling me that this is linearly independent. Is that even possible in this case? Right? No, it's not even possible. The max number of pivots I could even get here is 2. Right? I can't have 4 pivots if I've only got 2 rows, right? You can only have 1 pivot per row, right? If I've only got 2 rows, I can only have 2 pivots at most, right? So in this case, because S is, because there is no pivot in calls 3 and 4, S is linearly dependent. Okay. Now hopefully that makes sense, right? Like this is a subset of R2. It shouldn't take 4 vectors, right, to get all of the directions in R2. I just should only need 2 of them, in fact. Right? So 2 of those vectors are going to be redundant. Okay, assuming any of them are linearly independent. If any 2 are linearly independent, then the other 2 will naturally be can be written as linear combinations of the 2 linearly independent ones. Okay, and so this prompts like a nice corollary. You start to see some of the really great structure of this idea of linear independence in this corollary, I think. So if S is any set in Rn, right? Any set in Rn containing k distinct vectors where k is less than n, or sorry, other direction, where k is greater than n, then S is linearly dependent. Okay, so if S is any set in Rn containing k distinct vectors where k is a larger number than n, then S is linearly dependent. So in this previous example, n was 2, k was 4. I had 4 vectors in R2. At most, 2 vectors is what's needed. 2 independent vectors, right? You definitely don't need 4, right? So 2 of these, at least 2 of these, are linear combinations of the others. Okay, all right. So that's a nice corollary. So we've got 2 big theorems left, and I think what I'm going to do is I think I'm going to pause the video here. We'll have a part B so that we can address the other 2 theorems without fear of making the video too long. So let's go ahead and I'll pause the video here, and there'll be a part B. So hop on to the part B for the rest of the details.